In this video, we're going to examine how charges behave around a p-n junction, and we'll discover that they form an electrical bilayer called a depletion region. As a fun fact, this bilayer behavior occurs in lots of different contexts, including battery electrodes and cell membranes. So pay attention, maybe you can apply this lots of other places too. On the left of this slide, I've drawn p-type and n-type semiconductors at the very first instant that they make contact over here. This is a moment that never really exists, but it shows native p-type and n-type semiconductors right next to each other, which highlights the differences between them. In each semiconductor region you can see the fixed dopant charges, which can't move because they're stuck in a lattice. And they're surrounded by majority charge carriers that have been introduced by the dopants, so holes on the p-type semiconductor and electrons on the n-type semiconductor. And in addition, each side has a few minority charge carriers, like this sneaky electron, that have been thermally generated. These minority carriers usually aren't long for this world because electrons annihilate with holes when they run into each other, turning just back into a stable bond. But random motion will keep producing new minority carriers, so there's always a few. The right side of this slide shows what happens after the two materials settle into equilibrium. The big pile of holes in the p-type material will tend to randomly move into the n-type material, and vice versa for electrons in the n material. This process of random motion of carriers from high concentration to low concentration is called diffusion. And the interdiffusion of carriers results in lots of annihilation, which just leaves the fixed dopant charges behind in a region right centered on the junction. These dopant charges have an electric field inside of them, pointing from the positively charged phosphorus dopants to the negative boron dopants, and that electric field eventually cancels out the effects of diffusion. We'll formalize the descriptions of fields, charges, and carrier flows soon, but for now we'd just like to give a name to this special region of fixed charges. Typically it's called the depletion region, because it's been depleted of free charge carriers. It's also sometimes called the space charge region because there's some charges that are floating in space. We can be more specific about the electric field in the depletion region by making some assumptions about the charge distribution. It's common to assume that the doping profile in the region is uniform and infinitely sharp, which results in the net charge distribution shown in the upper right. This is called the full depletion approximation. Outside of the depletion region, so over here and over here, there's no net charge because there are equal numbers of fixed dopants and free charge carriers. Inside the depletion region, the absence of free charge carriers means that we have a net charge that matches the polarity of the fixed dopants. So the p-type semiconductor at negative x has a negative net charge because of the fixed boron dopants, and the n-type semiconductor at positive x has a positive charge because of the phosphorus dopants. I've chosen to draw the height and the width of the depletion region, so the height of the charge density and the width of the depletion region, as different on either side of the y-axis. And that's reflecting that the different sides of the junction might have different dopant densities. However, the depletion region was formed by free charge carriers annihilating one another, and each free charge is associated with a single fixed dopant atom. So that means the total charge on either side of the junction has to be the same. And therefore, the weakly doped side of the junction will be much wider than the heavily doped side of the junction, because the width times the dopant density has to equal the same charge on each side. Calculating that exact width is involved, so we're not going to be doing it in this class. However, while we're counting charges, it's worth noting that the units on this require some attention. Even though we're drawing a 1D plot of the net charge here, we're actually talking about a three-dimensional chunk of material. So representing the actual total charge in the material would mean these plots would change with the y and z dimensions of the junction, as the total amount of charge changes with the size of the material. So this plot usually just has a charge density on the y-axis. We can integrate the charge with respect to x to find the electric field in the depletion region, and it turns out to be this negative-shaped triangle. Because we're integrating with respect to x, we'd expect the electric field to point in the positive x direction for positive values of E, However, E is always negative, which means the electric field in the junction points in the negative x direction, so that way. That makes sense because we expect electric field to point from positive charges to negative charges, and our positive phosphorus dopants are in the positive x, and our negative boron charges are in the negative x. So our E field points from positive to negative, which is in the negative x direction. Seeing this E-field plot ought to excite you because it answers one of the fundamental questions we have about diodes, which is, why are they asymmetric? The E-field has a direction to it, so explains why current passes more easily one way in a diode than the other. It also explains why PN junctions are different than our model of resistive materials. We assumed that the only E-field acting on charge carriers in our resistive material came from outside, while PN junctions introduced some additional fields of their own. The field strength of this junction is pretty high, usually a few megavolts per centimeter at its peak, which is right at the transition between P and N-type material. Sharper doping profiles result in bigger built-in E fields, so that means E peak will be higher if the height of this charge density is higher. And as you might guess, if the E field gets big enough, then things inside the semiconductor can break down. We'll talk more about that later. Finally, we can integrate the E field with respect to x, which gives us a voltage. You're always free to pick what you're measuring voltage relative to. In this case, we set the voltage on the P-type semiconductor to be our ground, so we call it 0 volts. We can see that the built-in electric field results in a built-in voltage across the PN junction, and I've labeled it VBI. VBI can be used in some sophisticated math to predict properties of the junction, but be careful not to oversimplify diode modeling and use VBI for something it's not supposed to do. We're only going to use it one more time in this class, and it's just to justify something in the next video, so you mostly won't be including VBI in your equations. So in summary, a PN junction in equilibrium has a region of fixed charges called the depletion region. The fixed charges in the depletion region create an electric field that points from N to P. And the direction of this electric field is why diodes have asymmetric IV properties.